Good day, class. I am Mr. Okore Michael. I'm here to take you on physics. And today we are looking at gravitational field as a topic. Under the theme, field at rest and in motion. I want to ask for one thing, your attention, and if you give it to me, I promise you this class will be very interesting. First of all, we have to start by educating ourselves on the objectives of this topic. 1. By the end of this class, we should be able to understand the concept of gravitational field. Don't forget, the topic is gravitational field. Also, we should be able to know the gravitational force between two masses. We should be able to differentiate or know the gravitational force between two masses. Again, we should be able to say or understand the relationship between the force of gravity and the gravitational constant. Furthermore, at the end of this class, by the end of this class, we should be able to know and state the Keplers law governing planetary motion. And finally, we should be able to know the difference between natural satellites and artificial satellites. By way of introduction, I'll start first of all by defining or explaining what gravitational force is. I know we've heard about forces before now. I know also, that we have two types of forces. We have contact force and we have field force. But gravitational force is one of the field forces. Others are magnetic and electric forces. Gravitational force here we are looking at is the force of attraction between all masses in the universe, especially the attraction of the Earth mass for bodies near its surface. The more remote the body is, the less the gravity. What are we trying to say? The force of gravity is a force that exists between bodies that have what? Mass. For instance, the Earth is there, the Sun is there, the Moon is there. The gravitational force is what helps the Earth to exert force on, say, the Moon. The Moon is about 385,000 kilometers away from the Earth. There is no contact between them, yet there is this force of attraction due to what? Gravity. The Sun is able to exert a certain gravitational attraction or pull on the Earth, which is about 150 million kilometers away from it. These are all possible by the force of what? Gravity. Also, there is a law governing the force of gravity, or what we are going to look at today as a gravitational field. That law was put together by Sir Isaac Newton. It is called the law of gravity, or gravitational what? Law of motion. The law states that the force of attraction between masses is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. For instance, if we have two masses, say this is the Moon and this is the Earth, there is a distance between the center of the two bodies, which is called the R. That is to say, the force is proportional to the mass and inversely proportional to the square root of the radius. That's the distance between them. Now, gravitational force is a type of field force, as I said earlier. It is different from contact force. Now, what is a gravitational field? A gravitational field is an area, is a region where a body experiences a gravitational force, or where a body experiences a gravitational pull around it. That is to say, the location around a body where another body is able to influence it is what we call the gravitational field. We are looking at the gravitational force between two masses. Now, what is gravitation? Gravitation is simply the force of attraction exerted by a body on all other bodies. First, a body on all other bodies in the universe. Here, it may be interesting for us to take the Sun as the pivot body, occupying the central position, and every other planetary body is surrounding it in an orbit. Say the Earth is somewhere here. Gravitation is that force that the Sun exerts on the Earth as well as other planetary bodies. It says the force of attraction exerted by a body on all other bodies in the universe. Remember, mass must be involved for gravity or gravitational force to take place. It exists between a body and all other bodies around it. Earlier on, I defined or explained what gravitational field is. Now, if this is the sun and this is the earth here, the space between them is where the gravitational field lies. And because the sun is able to exert a force around this field, it is able to attract the earth to itself. A typical example of this approach is seen in Newton's law of universal gravitation, which we stated earlier that the force of attraction is directly proportional to the product of the masses of the bodies and inversely proportional to the square of the distance between them. Mathematically, you can say it is proportional to m1, m2, where m1 represents the mass of one of the bodies and m2 is the mass of the second and r the distance between them squared. Now, if you remove this sign, this proportionality sign here, you have F is equal to G, capital letter G, m1, m2 over r squared, where this capital letter G is a constant, replacing this proportionality sign, and is called gravitational constant. Now, let's look at a few calculations involving Newton's law of gravity. First, what is a gravitational force acting upon two objects of masses 15 grams and 15 kilograms that are 11 meters apart? Now, I underline these masses so that you know what we are working with. Of course, you should also remember that the standard unit for measuring mass is what? Kilograms. That is why it's important, before you go into this calculation, to convert these grams to kilograms. And how do you do that? To convert grams to kilograms, you divide by 1,000. That is to say, 15 divided by 1,000 will give us 0.015 kilograms. Here, the gravitational constant G is given because it's a constant, and you have to memorize the constant. You have to know the constant. It is 6.67 times 10 to the power minus 11, and the unit is a Newton meter squared per kilogram squared. I repeat, the capital G, which is constant gravitation or gravitational constant, is a standard with a specific unit, 6.67 times 10 to the power minus 11, and the unit is Newton meter squared per kilogram squared. It's also on the board. Now the mass, the M1 is 15 grams, which converting it to kilograms gives you 0.015, which I wrote here, kilograms. And M2 is already in kilograms, which is a standard unit for calculating mass, so you don't need to change it, 15 kilograms. The R, which is the distance between the two masses, is given to us as what? 11 meters. You note it. Then coming again, what is force? Force is equal to G times M1 times M2 over R squared. Now, putting these values there, the force we're looking for is the G, which is 6.67 times 10 to the power minus 11 times the first mass M1, which has been converted to kilogram, 0.015 times the second mass, 15 kilograms, divided by 11 squared. Remember, the R is squared. And 11 squared is 121. By the time we divide this out by 121, we can do a further calculation here, where we have 6.67 times this going into this will give us 2.25 times 10 to the power minus 11 times 10 to the power minus 3, dividing it by 121. At the end of the day, we're having force is 1.24 times 10 to the power minus 13 Newton. Newton is the SI unit of force. Remember, whenever you're doing a calculation on force, you must remember the unit, and Newton is the unit of force. Still on the same topic, we are continuing by second calculation. Two satellites orbiting Earth pass close to each other. For a moment, they are 100 meters apart, and the masses of the satellite are 300 kilograms and 20 kilograms. What is the magnitude of the force of gravity between the satellites? Here also, we're looking for the force. And remember, the gravitational constant is also needed. Then the masses, the first mass is 300 kilograms, the second mass is 20 kilograms. And the distance between them, which is the R, is 100 meters, according to the question. What do you say? F is equal to G M1 M2 over R squared. Inputting the values, we have 6.67 times 10 to the power minus 11 times 300 times 200 all over 100 squared. 100 squared will give us 10,000. So when you work out this, 20 times 300 gives you 6,000. 6,000 times 6.67 times 10 to the power minus 11 all over 10,000 will give you 4.0 times 10 to the power minus 11 Newton. Also remember that the unit of force is Newton. All other units will cancel out and you have Newton as the last unit because we're looking at what? Force. Now the magnitude of the gravitational force between the two satellites when they are 100 meters apart is 4.0 times 10 to the power minus 11 Newton. So whenever you are asked to do a calculation that involves the force of gravity, just remember the formula. F is equal to G, remember it's capital G, which has a constant value of 6.67 times 10 to the power minus 11 times m1, m2 all over r squared. Going further, we're looking at acceleration due to gravity and the gravitational constant. Is there any relationship between these two? Yes. Now, by the use of Newton's law of gravitation, the mass and density of the Earth can be estimated. And if we can estimate the mass and density of the Earth, it will help us to get the relationship between the force of gravity and acceleration due to gravity. Remember, the gravitational constant is symbolized or denoted by the letter G, capital, while the force acceleration due to gravity is by letter G for small letter. Now, the small letter G is acceleration due to gravity. It's also a constant, 9.8 meter per second squared. And the radius of the Earth, in this case, we're using 6.36 times 10 raised to the power 6 meters, which is about 6,384 kilometers, or 380 kilometers. The universal gravitational constant is 6.67 times 10 to the power minus 11 Newton meter squared per kilogram squared. We are now conversant with this constant, I want to believe. Now, going by the formula according to Newton, F is equal to G m1 m2 over r squared. Thus, the mass of the Earth. Let's do a little calculation here using change of subjects, where ME is the mass of the Earth and RE is the radius of the Earth. Remember, the R is squared. From here, you can cross multiply this and have from here, we can say G or M, since we're looking for mass of the Earth, mass is what? FRE squared over Gm. And where the mass of the Earth is equal to the ratio of the force times the square of the distance divided by the gravitational constant times the mass. Now, what is force? Simply put, force is simply mass times what? Acceleration due to gravity. If we apply that, we have mg RE squared over Gn, where m will cancel m. Therefore, the mass of the Earth is simply G, small letter G, RE squared over capital G. Now, this is the mass of the Earth. From there, we can now deduce. We can deduce the relationship between the capital G, which is gravitational constant, and the small g, which is acceleration due to gravity. By so doing, we come to the point where we say capital G is equal to small g RE squared over mass of the Earth. And the small g is simply capital G times mass of the Earth over R squared E. And this is the relationship between the small g and the capital G. Now, looking at the next topic is gravitational potential. Gravitational potential is symbolized by the letter what? V. Is a point of a point because we describe or we discuss gravitational potential at a given point. And the gravitational potential at a given point is different from another point. So the gravitational potential at a point, at a particular point, is the work done in taking unit mass from infinity to that point. Underline the word infinity. The work done in taking a unit mass, underline the word what? Unit. Unit means one. The work done in carrying per se 1 mass, 1 kilogram, 1 gram of a particular body from infinity, from a far distance to where? To that particular point. That is what we describe as gravitational potential at that point. The unit is joule per kilogram. Joule, why? Because we're talking about work done. And the unit of work is what? In joule. Why? The mass of the body, remember, is unit mass. That is why we're saying per kilogram. The work done, that is in joule, in moving or in carrying a body of unit mass from infinity to a particular point. Remember, the SI unit of gravitational potential is in joule per kilogram. Now, points in any gravitational field possess gravitational potential. At every point in a gravitational field, there is a gravitational what? Potential. There is work needed to be done. To calculate gravitational potential, what do? There is a formula for doing that. And the formula is what? Gm over R. Now, what is G? That is to say, gravitational potential is simply gravitational constant times the mass of the object. Remember, is a unit mass over what? The distance where you are moving it from to the point. The distance between infinity and the point. Of course, G is a constant. M is the mass of the object, while R is the distance. We are not squaring the R this time around. We are just looking for just the R is what we use. It decreases as R increases and becomes 0, where R is infinitely large. It decreases as R increases. Why? Because R is acting as the denominator. When the R is large, the value of the gravitational potential reduces. For instance, if Gn is equal to 10 per se, and our R is equal to 2, the gravitational potential V will give us 10 over 2, which is what? 5. Now, if the R increases to 4, we'll have V will give us 10 over 4, and the answer is what? 2.5. That is to say, as the R, the distance between the objects increases, the gravitational potential decreases. And vice versa, as R decreases, gravitational potential increases. The negative sign you see here, minus Gm over R. The negative sign is just to show us an indication that the potential at infinity is higher than the potential close to the mass. The potential at where infinity, that's what we just said, the farther it is, the more you have it. As you come closer to it, the potential decreases. And that is why we give it a negative value, or a negative value is assigned to it. Now, let's look at this calculation based on gravitational potential. It says find the gravitational potential at a point on the Earth's surface. Take mass of Earth as 5.98 times 10 raised to the power 24 kilograms. Its radius as 6.38 times 10 raised to the power 6. And let the gravitational constant be the same, 6.67 times 10 raised to the power minus 11. Now the solution, V is what we're looking at, Gm over R. G, the gravitational constant, is 6.67 times 10 to the power minus 11 times the m, which is the mass of the Earth here, 5.98 times 10 to the power 24, divided by the distance, which is the radius of the Earth, 6.38 times 10 to the power 6. Dividing this out, the gravitational potential will give us 6.25 times 10 to the power 7, not forgetting the unit, joule per kilogram. Not forgetting the unit, joule per kilogram. The next thing on the line is escape velocity. What is escape velocity? Now, when an object is moving around the Earth or revolving in a given orbit, a time comes when it pulls away from that orbit. A time comes when it escapes. Now, there is a minimum velocity required for an object moving around an orbit to leave that orbit. That is simply what we call escape velocity. Now, let's put it this way. Escape velocity, VE, is the minimum velocity required. The minimum velocity required. You can call it the threshold velocity. The least amount of velocity required. The smallest amount of velocity required. For an object, example, satellite or rocket, to just escape or leave the gravitational influence of an astronomical body, example the Earth. We said that the Earth exerts a force upon all other bodies around it. Now, how do these other bodies escape the influence of the Earth's gravity? It is when they are able to acquire this minimum velocity, they can now increase their velocity and escape from the influence of the Earth's gravitational pull. Now, that is what we call escape velocity. It can be calculated as well using the formula VE is equal to, it is square root of 2gr, where the g there is acceleration due to gravity, and the capital R is the radius of the Earth. Let's look at this calculation involving escape velocity. Calculate the escape velocity of a satellite from the Earth's gravitational field. Here we are given that g is 9.8 meters per second squared, and the radius of the Earth here is 6.4 times 10 to the power 6 meters. Now v, as we know, is root 2gr. Now that is to say root 2 times 9.8 times r, which is 6.4 times 10 to the power 6. Multiplying out, you are having the square root finally gives you 11 times 10 to the power 3. And the unit is meter per second. Remember, it is velocity. And velocity is measured in meter per second, which is simply 11 kilometers per second. That is the minimum energy required by this particular satellite, or minimum velocity required by this satellite to leave the gravitational influence of the Earth. Any velocity less than this cannot allow the satellite to escape from the gravitational pull of the Earth. But anything higher than this, upward, will do that. Again, we are looking at Kepler's laws. Kepler is a scientist who studied the planetary motions, how the planetary bodies revolve around the sun. Per se, he delved into the solar system and the motions in the solar system. He came up with 3 basic laws, which we are going to look at one after the other. The first law of Kepler says the planets each travel along an ellipse with the sun at one focus. All of them travel at an ellipse. An ellipse is a pathway that is curved. You can say it is parabolic. At the end of the day, it forms a circular path, which each of them take. Of course, if you go to the solar system, you see this movement around the sun. Going back to the second law of Kepler, it says that the line joining the sun and the planet sweep out equal areas in equal time. What it simply means is this: since the sun occupies the central position in the solar system, the other planetary bodies revolving around it at every point in time, wherever the other body is, as exemplified by this diagram here, the radius between the body and the sun is the same. As the body keeps going around, the radius is always the same. The distance between them is constant. Then, going to the third law, the third and the final law, is that the square of the period of revolution of planets are proportional to the cube of their mean distances from the sun. It means that at the time it takes a body to go around the sun is proportional to the cube of the distance between them. What does that mean? For instance, the Earth, which is closer to the sun than maybe Pluto, will have a shorter time to go around its orbit than Pluto will have. For instance, Mercury, which happens to be the first planet, takes just 88 days to go around the sun, while the Earth, having a higher radius, takes 365 days to go around the sun. That is to say, the time, which is a period of revolution, taken to go around the sun is proportional to the what? The mean distance between that object and the sun. As the distance between the object and the sun increases, the time of revolution also increases. That brings us to natural and artificial satellites. What are natural satellites? Most times, if you come out in the night, particularly this period we are in, if you look up the sky, you see the moon shining. The moon is a typical example of a natural satellite. In fact, natural satellite, it is known as the moon and is a celestial body that orbits a plane or smaller body, which is called the primary plane. It goes around a plane. It's a satellite. It is there. Now, the moon is the Earth satellite and is a natural what? Satellite. Remember what I told you earlier? That the moon is about 385,000 kilometers away from the Earth. Yet, the Earth is able to exert a gravitational pull on it. Now, artificial satellite, the moon, before I go on, is about the only known natural satellite. And the moon of the Earth is the biggest satellite among the planetary bodies. Then artificial satellites, these are man-made or human-built objects orbiting the Earth and other planets in the solar system. Today, we hear of so many satellites out there. One, they help in communication, they help in getting information, and they help in other activities of man. Artificial satellites are not like the natural satellites. They can be mounted anywhere. Remember, they are human-built, they are man-made, they are not natural, but they are up there, orbiting also, just like the natural satellites, going around the plane as well. In summary, let's go back to where we started from, gravity. Gravity is a dominant force in the universe, where energies are low and volumes are large. Gravity is a dominant force in the universe. What that is to say, it is just there. Gravity is what makes it possible for you to come down whenever you jump up. Gravity is what brings you back to the center of the Earth. And if you get to anywhere where there is no gravity, if you go up, I doubt if you can come down. Also, gravity can be reduced. How do you reduce gravity? Remember, by moving far away from the massive objects. But it can never be eliminated. No matter how you do, you can only do what? Reduce it. Remember, we said earlier that the longer the distance, the less the gravitational force. But you can only do what? Reduce it. You cannot completely eliminate it. A gravitational field is a region in which masses will experience a force. It's a region. It's not just a point. It's an area where a particular mass experiences gravitational force or pull. But we are not concluding this class without going back to maybe one or two questions to see if we actually understand what we've been taught today. First, Newton's law of gravity states that the gravitational field between two bodies is dash. A, inversely proportional to the product of their masses and directly proportional to the square of the distance between them. B, proportional to the product of their masses and inversely proportional to the square of the distance between them. Inversely proportional to the product of their masses and inversely proportional to the square of the distance between them. This proportional to the product of their masses and proportional to the square of the distance between them. The correct answer is B. It is proportional to the product of their masses. F, remember, is proportional to m1, m2 over r squared. It is proportional to the product of their masses and inversely proportional to the square of the distance between them. 2. An experiment to measure the force of gravity is set up using two large spheres. The spheres are both 1,000 kilograms and the centers of mass are 2 meters apart. What is the force of gravity between these two spheres? We're looking at the force of what? Gravity between these two spheres. We can do small calculation here. F is equal to G m1 m2 over r squared. Where G is 6.67 times 10 raised to the power minus 11. And we have m1 is 1,000, m2 is also 1,000. So we can say 1,000 squared all over r. The r is 2 meters apart, which is 2 squared. This gives us 6.67 times 10 raised to the power minus 11 plus 1,000 squared will give us 1 million, which is 10 to the power 6 divided by 4. 2 squared is 4. This is simply dividing 6.67 by 4. We have 1.6675 times 10 raised to the power minus 5. The answer is C. Having done this class, I want to believe that we've been able to achieve something today. I know after today, you can comfortably say, I've done gravitational field, where you can be able to state the Kepler's laws and be able to do some calculations involving gravitational field. Until we meet next class, where I'll be discussing more interesting topics. It's bye for now.